Welcome to podcast 17.1, first one for chapter 17, where we're going to take everything we know about Le Chatelier's principle, weak acids, weak bases, calculating pH, and put it all together and apply it to some pretty cool situations, systems that happen in your bodies, happen in nature, these things called buffers and buffer calculations. We'll be figuring out what those are, looking at titrations with a little bit more detail, and something known as KSP, the solubility of insoluble things. How do we know when a precipitate is going to form and under what conditions and that sort of stuff. So let's set up the background for this information by revisiting Le Chatelier's principle, which, if you remember, says that if you have a system at equilibrium and you apply some sort of stress to it, the system will shift in a direction that will restore its equilibrium. So usually creating more reactants, sometimes creating more products. And since we're dealing with weak acids and weak bases, we're going to be looking at, the ionization of those weak acids and weak bases. How do we get more H plus ions? How do we get more of the weak acid molecule and that sort of stuff? We apply what is known as the common ion effect, that if we mix in a salt of a weak acid or a weak base, what will that do to our system at equilibrium? And probably the most confusing things for folks to realize is that we're not talking about a reaction, that it's actually adding in one of the ions that already exists at an equilibrium. So for instance, we have a weak acid here, hydrofluoric acid, and a ionic compound, sodium fluoride, which if we put sodium fluoride in with hydrofluoric acid, your first instinct is to kind of create it as some sort of like double displacement or something reaction, but that's not what's happening. Go back to chapter 4 and think about what happens when you put an ionic compound in water. It ionizes, right? So we get sodium ions and we get fluorine ions. So when you put these things in water, really what you have is a concentration of ions. Well, acid-base chemistry is wet. Everything is in solution. So if I have a solution of a weak acid, hydrofluoric acid, and I get these H ions and F ions, if I add in sodium fluoride, some solid sodium fluoride, and it starts to ionize in the solution, really what I'm doing is I'm increasing my concentration of fluorine ions. So according to Le Chatelier's principle, what is going to happen? Well, my concentration of hydrogen ions is going to go down, which means my concentration of the weak acid is going to go up, so this reaction is going to shift towards the reactants. So when we talk about common ions, think in terms of the acid and its conjugate. What is its partner? Look at that, that little ion. So when you have acids, you have some sort of ic acid, and we're mixing it with some sort of 8 ion. Keep in mind, how do you name and write those formulas? If it's nitric acid, its partner is the nitrate ion. So oftentimes we're going to be mixing some sort of ic acid with some sort of 8. Formic acid with sodium formate, acetic acid with sodium acetate. We could do this, I keep saying sodium, but sodium's pretty soluble because we all know our solubility rules, so you'll see that quite a bit. So what is a buffer solution? So that when we have these common ions, we create what is known as a buffer solution. A buffer, by definition, is something that resists a change in pH when small, keyword there, small amounts of acids or bases are added. We can kind of go either direction, but anytime you have something that maintains a kind of a constant buffer, and there's lots of examples in nature. Seawater is one big happy buffer system. Your blood is one big happy buffer system. So there's lots of living organisms that depend on a constant pH. So for instance, like seawater, it kind of needs to be in a pH between 7.5 and 8.4. Your blood needs to be about 7.38, and it really can't handle any pH above or beyond that. So it has what is in place known as a buffer solution, where you have some sort of weak acid and its conjugate and its salt. So that's how you create a buffer solution. You know if you have a buffer because it is a mixture of a weak acid and its conjugate, or a mixture of a weak base and its conjugate. So again, you kind of think in terms of its pairs, and really you can use Le Chatelier's principle to think about how these systems really work. If you put a little concentration of the salt, it's not going to have the. So for instance, if I kind of let's look at this example. If I put in, so this is my bicarbonate ion right here. If I put in some little concentration of this particular salt, it's not going to have, and if I add any acid to it, it's not going to have anything to react with. By the same token, if I put in some sort of base, the base will actually kind of act to remove this hydrogen ion. And so the equilibrium is going to shift to kind of replace that. So it'll remove the hydrogen ion to form water. Because remember what happens when we add an acid and a base, you get salt and water. So that's what a pH does. If you kind of look at the overall system, you get very minimal changes in your concentration of hydrogen ions if you add an acid or a base. How do we make a buffer? Well, there's a couple simple ways to kind of do it. Sometimes the exams will ask you questions like, well, how would you prepare a buffer solution for this particular situation? The easiest way is to simply mix a weak acid or a weak base and its conjugate in about equal-ish proportions, something like that. 2 parts weak acid to 1 part strong base, you would actually create a nice little buffer solution. The other way that you can do it, and this is a little bit more common because this is what we do with titrations, is you partially neutralize a weak acid. And again, or a base, but we're going to kind of focus on acid since that seems to be a little bit more common with a strong base. Really what we kind of do is we choose some sort of acid with a Ka that's close to our desired pH that we're trying to maintain and add equal parts to it. So when you do a titration, when you start to look at those solutions in a little bit more detail, which we will, as soon as you start adding those first drops from the burette, you have created a buffer solution. Other questions may ask you about something known as the buffer capacity. This is just, to what extent will your buffer solution maintain its pH before you get a drastic change. And so really the easiest way to kind of figure out buffer capacities is by looking at your Ka. So for instance, if you wanted a buffer with a pH of 3, your acid, your conjugate base pair, you're going to pick a Ka that has an exponent to close to -3. Or if you know the pKa, same kind of idea, because pKa is the negative log of your Ka, you're going to get one that's close to 3. So you may see some questions that deal with that. Okay, the calculations piece can be tricky for some folks, but really success will be yours if you kind of understand a few little concepts. In other words, the conjugate acid-base concept. If you know, if you can identify what lost the proton and what gained the proton, that's going to be a huge piece to understanding buffers. If you know that Ka times Kb equals Kw, and most folks when you ask them, okay, what does Kw mean? And they're like, oh, I know what that is. It's 1.0 times 10 to the negative 14th. Yay! That's a big piece of it, but also kind of understanding that this is also related to your concentration of hydrogen ions and your concentration of hydroxide ions. So if you can kind of keep that in the back of your head, you'll never be asked to memorize Kas or Kbs, but I would definitely know Kw, 1.0 times 10 to the negative 14th. It's concentration of hydrogen ions times your concentration of hydroxide ions. The other piece is how do you calculate pH? Remember that if you know your concentration of hydrogen ions and you take the negative log of it, that gives you your pH. So with those little tidbits in mind, let's take a look at how we solve buffer calculations. Okay, so let's start off with something that we've already looked at. How would we figure out the pH of a 0.1 molar solution of acetic acid given its Ka? So let's set it up using our friend the icebox. First thing that I'm going to do, of course, is write out my balanced equation. With all of these things, I always write out my equation. This is how I'm going to organize my information It also just kind of gives me a picture of what is going on. So, of course, all this stuff is wet chemistry. We're going to be putting it in water. How does it dissociate? So there's my reaction. All right, let's set up an icebox. Weak acid, so I need to know what happens to my concentrations when they come to equilibrium. I start with a 0.1 molar solution of acetic acid. Now, since this is water and liquids are not included in my Ka expressions, I don't care about that. 0, 0. How is this going to change? I don't know, so let's call that x. So what equilibrium I have that? This is going to go up by x, up by x. So at equilibrium, I know I have x and x. Okay, so far so good. Let's plug this into my Ka expression. Okay, products over reactants, so I'm going to have x times x divided by 0.10 minus x. You have to know the Ka. It's going to be somewhere in the problem, or there's a big table in the back of your textbook. You can always look it up, but on exams, you'll be given that piece of information. And now we can go ahead and solve for x. So remember our little shortcut that we assume that the change of our initial concentration is negligible, like it hardly changes at all. So I can just kind of ignore that x. And that made my math a whole lot easier. And so I come up with an x value of 1.8 times 10 to the negative fifth. Okay, I lied. It's not 1.8 times 10 to the negative fifth. Erase. Erase. There we go. When I go ahead and solve for x, I end up with 0.00134. Now, what does this tell me? Well, x in this case is my concentration of hydrogen ions. So now I need to calculate pH. I'm going to put this up here because I didn't give myself enough room. And remember that pH is my negative log, my concentration of hydrogen ions. So if I do the negative log of 0.00134, I get a pH of 2.87. And that should make sense because I'm dealing with a acid, so my pH should be in that range. Now, word about significant figures and logs. Since I have two significant figures in my given, I want to make sure that in my pH I have two decimal places. So that's how that kind of matches up. You look for your significant figures in your given, and that kind of equates to the number of decimal places you should have in your pH. Alright, moving on to a mixture that contains 1.0 molarity acetic acid and 1.0 molarity sodium acetate. So there's that 8-ic combination. So let's write out our equation and get a picture of what we're doing. I'm just going to rewrite my ionization down here. This time I'm going to not put in the water because we don't care about that piece. And show it with the H+ ions. Either way is acceptable. Know that in real livesies there's that hydronium ion, but for simplicity's sake we'll just kind of keep it as H+. Okay. Now this time I know I have a 0.10 molarity acetic acid solution. But I have another piece of information, sodium acetate. So sodium acetate, an ionic compound, you put it in water, it completely ionizes. So what that does is that gives me an initial concentration of acetate ions. I have no hydrogen ions at this point. So that's what I do with that information. It's not a reaction. Don't try to do any sort of weird synthesis or double displacement or something like that. You are adding in the common ion. So now let's fill out our rest of our equilibrium tables. This is going to go down by x. That's going to go up by x. This side is going to go up by x. Remember, your products always go up. Your reactants always go down. I now know my equilibrium concentrations. And I can plug it into my Ka expression. It's the same acid as in part A, so my Ka is still 1.8 times 10 to the negative fifth. So I've got x times 0.1 plus x divided by 0.1 minus x, and this is all equal to 1.8 times 10 to the negative fifth. Okay, the same little shortcut that we applied earlier with assuming that change is negligible, we can apply here. So we can really simplify this equation by saying, okay, my little changes aren't going to be that much because this is a weak acid. My exponent is like 10 to the negative fifth, so that's less than 1%. So I can simplify my expression to be this. Just kind of ignore those other little x's. Go ahead and solve for x this way. And I get 1.8. This time I get 1.8 times 10 to the negative fifth. So that's my concentration of hydrogen ions. X in this case equals my concentration of hydrogen ions. Now to figure out my pH, pH is a negative log of that information. So negative log of 1.8 times 10 to the negative fifth gives me a pH of 4.74. Does this make sense? Yeah. Okay, a little bit of an acidic solution, but since I added in that salt, I would expect a change in my pH. Let's do some more examples here as we kind of get the hang of this. So if I kind of mix up our volumes and molarities a little bit, 50 mils of 0.5 molar sodium acetate mixed with 25 mils of 0.25 molar acetic acid, what are we going to get? As we do these buffer calculations, the first thing that you always kind of want to ask yourself is which equilibrium is the source of hydrogen ions? Because most buffer calculations are going to have you say, what is the pH? So pH, you need hydrogen ions. So the equilibrium that I care about is the equilibrium of my weak acid, not the dissociation of the sodium acetate. Now what the dissociation of the sodium acetate does is it gives me a concentration of acetate ions. So since I've got two different molarities and two different volumes, volumes of course are additive, the first thing that I have to do is go to the mole. I must convert to moles. So I'm going to figure out how many moles of this I need, or I have, and how many moles of this I have. So remember that molarity is moles per liter. Now since volumes are additive, when I mix these two things together, I'm going to have a new volume of 75 milliliters. So my first step is going to be figure out how many moles of sodium acetate I have and how many moles of acetic acid I have. So I end up with 0.025 moles of this stuff. Kind of doodling off to the side here. And I end up with 0.00625 moles of my acid. Now my icebox is, since I need concentrations, I'm going to have to put this into molarity. So you divide it by your new volume. So this ends up being 0.0833. This is 0. This is 0.333. Change. It's going to go down by x, that's going to go up by x, that's going to go up by x. So this is now 0.0833 minus x. This is x. This is 0.333 plus x. Let's plug it into our Ka expression. Products over reactants. And I know my Ka, 1.8 times 10 to the negative fifth. Apply the same shortcut that says our change is negligible, so we can clean this equation up, make our math a whole lot easier. Now really I should check myself by figuring out percent dissociation, but the majority of the exams do not give you funky exceptions that go beyond that, so I wouldn't worry too much about that. So then I go ahead and solve for x, and I end up with 4.50 times 10 to the negative sixth. So what does x mean? X is my concentration of hydrogen ions. So now I'm good to figure out what my pH is. pH is negative log of 4.50 times 10 to the negative sixth. And so my pH comes up to be 5.34. All right, now there is an easier way to do this if you recognize what you have is a buffer solution. A buffer solution means you've got those combinations of the ic acid and the ate ion, where you've got those conjugate acid-base pairs. The cool equation of which I speak is called the Henderson-Hasselbalch equation. And it looks a little something like this. I can figure out the pH of a buffer solution by taking the pKa, so that's the negative log of the Ka, plus the log of your base, which is usually we're talking about your conjugate base, divided by your concentration of the acid. So let's apply this to the example number 2 that we just looked at. How do we figure out our pH? Well, I need to know my pKa. So that means I'm going to take the negative log of 1.8 times 10 to the negative 5th. I'm going to add to that the log of my concentrations of the acid and the base. So if you look at your ICE table from before, we have our concentrations. We have concentration of the base, that's the acetate ion, and my concentration of the acid right there. So I'm going to take 0.333 divided by my concentration 0.0833, and we simplify this. This gives me 7.52 plus, just showing a little math steps here, the log of 3.84, if I do that little division properly, and this ends up with a pH, oops, this is what happens when I mix two problems together. Okay, let me fix these numbers, because apparently I smushed two problems together. So log of negative log of 1.8 times 10 to the negative 5th, this is 4.74, plus the log of 3.96, which gives me a grand total of a pH of 5.34. And wow, that's the same answer as I got before. Isn't that cool? Love the Henderson-Hasselbalch. It works only for buffers, so you got to recognize that you've got the ick and the ate thing going on, or the us and the ite, I suppose. Let's do another example. pH of a hypochlorous acid, sodium hypochlorite solution. So it is a weak acid, and we have its conjugate base. So the first thing I'm going to do, of course, is write out my equation, my ionization. I gotta flip that in my head. Equation, what is taking place? So hypochlorous acid, and I'm adding to it potassium hypochlorite. So there's the us and the ite. So we've got the salt of the weak acid, the conjugate base of the weak acid. First thing that I gotta do, since I've got different molarities and different volumes, go to the moles. Convert to the moles. So I need to figure out how many moles of this I have. Turns out of the acid, this gives me 0.00375 moles. And how much of the hypochlorite I have. So this is going to be 0.0144 moles. And so again, how do I know that this is not some sort of reaction? Because potassium hypochlorite is an ionic compound. It dissociates completely, so it's ionizing completely. So what I have is a concentration of the OCl ion that I'm concerned about. Once I kind of recognize this, the other piece of information that I kind of need to know is the Ka of hypochlorous acid, which I've conveniently looked up for you, which is that. It's in the back of your book, but there you go. So we could do this with an ice box, but let's try our Henderson-Hasselbalch equation. pH equals pKa plus the log of your concentration of base divided by your concentration of acid. Now here's another little lazy shortcut that I like to take. So pKa, this is your negative log of your Ka. So negative log of 3.0 times 10 to the negative 8th. Now if we think about it, brackets are for concentrations, moles per liter. However, since I've got moles per liter divided by moles per liter, and I've converted both of my things into moles, my liters are canceling out. So really, all I need to do is the log of my moles of base divided by my log of moles of acid. And I do this, and I come up with a pH of 8.10. Ta-da! Let's do one more for good measure, this time looking at it from the base perspective. If I have some sort of ammonium ion, could be ammonium chloride or whatever, but chlorines are spectator ions, so I'm not worried about that piece. And I mix it with NH3, a weak base. How would I calculate the pH of this? So let's start first by setting up our little wet equation. If I put ammonia in water, I get ammonium chloride or ammonium ions and hydroxide ions. And what do I need for pH? I need a concentration of hydrogen ions. Since pH, I need a concentration of hydrogen ions, I've provided you with the Kb for ammonia. The other piece that I need to do, since I've got a molarity of one thing and a molarity of something else, I must go into moles. Hopefully you are hearing the sound of my voice. Convert to moles. So I'm going to figure out how many moles of NH3 I have. And I figure out how many moles of my ammonium ion I have. Now, is this a buffer? Yes, because buffers have equal-ish proportions of the acid and its conjugate base, or the base and its conjugate acid. So I look for the partners. 0.005 NH3, 0.005 NH4. This tells me I have a buffer, which means I can use the Henderson-Hasselbalch equation to figure out pH. However, the Henderson-Hasselbalch equation for pH says that I need the pKa. I do not have the pKa. I have a Kb. So if you remember, one of the other keys to success was recognizing the relationship between Ka and Kb. It equals Kw. So since I know my Kb, I can solve for my Ka by doing Kw divided by Kb. Plug in your numbers. 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. This gives me a Ka of 5.56 times 10 to the negative 10th. So now I can plug this into my Henderson-Hasselbalch equation. I'm going to take the negative log of 5.56 times 10 to the negative 10th plus my log of base, concentration of base divided by concentration of acid. Your volumes are going to cancel out, so I leave it in moles. Probably cheating, but it works. This gives me 9.26 plus 0, which gives me a pH of 9.26. And if you think about it, your answer should make sense. 9.26, this is a basic solution, so it's a reasonable pH. If you forget this Ka, Kb, Kw step, and you just plug in the number that you have there, you would end up with a pH of 4.74, and that would not be a reasonable answer for ammonia. That would be a reasonable answer for some sort of acid. So again, just kind of always check yourself. Does your answer make sense? And that is the magic of buffer calculations.